This is the second lecture in the electricity section on industry organization and supply. How was the electricity industry organized in the past? In almost every country around the world, the electricity industry used to be organized as a vertically integrated monopoly. That means that one firm owned the generation and the transmission lines, and sometimes even the distribution and retailing networks. This firm was usually, but not always, government owned. If it wasn't government owned, then it was regulated by the government. For the vertically integrated firm, ensuring cheap and reliable supply of electricity is an engineering problem. They manage the operation of the generation plants and the transmission networks in order to meet demand at lowest cost. And then regulators set the price paid for electricity, which may or may not have covered the cost of supply. So in other words, these firms may not have been making a profit, especially if they were government owned, and so there had to have been additional taxes to make up that difference. There has been a recent wave of changes to this industry model, however. Electricity generation used to be seen as a natural monopoly, where each city would have its own generation plant with limited transmission connecting all the cities. Today, though, the lowest cost method to meet demand may be from multiple small generation plants connected over a large network, even over multiple states. Many factors contributed to this change, including advances in generation technology, which reduced the economies of scale in the industry, where we now have some small plants like natural gas plants with lower marginal costs than large coal plants. And there's also advances in transmission and information technology that increase the distance over which electricity could be transmitted. So now we can transmit electricity from the East Coast to the Midwest in seconds, or less than seconds, in fact. An essential component in electricity restructuring is the introduction of competition in generation. So instead of a natural monopoly, we have competition in generation. We're talking about the wholesale electricity market. So instead of an individual generator like a coal plant, we now have many different natural gas and coal plants competing to supply a given market. Private profit maximizing firms might be expected to choose optimal location and technology for their plants, as well as optimize their fuel and labor inputs. This is in contrast to a monopoly, where the firms have no incentive to optimize their fuel and labor, etc. We would expect this to lead to lower costs for consumers, and that's the main thrust of why we see this restructuring of the markets is that economists suggested that competition would lead to lower costs for consumers. What else is required for there to be competition in electricity generation? With multiple firms, the coordination problem of when each plant should run becomes more complicated. Recall, we still need supply to equal demand each second and in each location. If the system is still managed by the vertically integrated generation and transmission owner, they might favor their own generation plants. For competition to work, the coordination of generation and transmission operations needs to be independent. So there's been a transfer of these roles to the independent system operator, or the ISO. The ISO is an independent organization that balances supply and demand in a competitive wholesale market. In summary, here are the components of the electricity industry restructuring. So the essential part of restructuring is the introduction of competition in generation and an independent system operator. So in contrast to a vertically integrated market with a monopolist producer, monopolist generator, the essential part is that we have introduced competition in generation into the wholesale market. The transmission and distribution remain natural monopolies oftentimes, they receive a regulated price for their services. Other aspects of restructuring in some countries. So retailing may potentially be competitive. This actually happens in the US sometimes, though the benefits from introducing competition are unclear at this point. at least at the retail level. Some or all of government-owned firms may be privatized. So some of the monopolists that existed in the past may be sold off to private companies. How do wholesale markets for electricity work? The ISO uses the wholesale market to coordinate the exchange of electricity. Market ensures that the lowest cost generation is used to meet demand each period, subject to generation and transmission capacity limits. There's a variety of sequential markets that operate at different timescales. There's forward markets. These are financial contracts between generators and retailers that exist for months or years in advance. So these are kind of like the futures markets in the oil industry, except these are forward contracts. So these are one-off contracts between generators and retailers for electricity supply months to years in advance. There's a day-ahead market, and this is scheduling of electricity production for the following day. This happens 24 hours in advance. Every hour of the day this is going on. So at 3 p.m. today, generators are supplying bids for 3 p.m. the following day, and then at 4 p.m. the same thing happens for the following day, etc. There's a real-time market, which coordinates generation of more or less electricity due to unexpected demand fluctuations. So this is happening, depending on the market, happens either at 15-minute intervals or 5-minute intervals. And then there's even ancillary services market, which is second-by-second balancing of the grid. This is having standby capacity online at any given time. So now we're really getting into how the wholesale competitive market works. Firms are submitting offers to generate electricity. Each day, every hour of each day, firms submit to the market operator, the ISO, their willingness to supply energy for each hour of the following day. The willingness to supply, or the offer curve, is a step function consisting of pairs of quantities and prices for every power plant. So here's an example. Firm 1 submits offers to generate electricity. Their offers, so these are different, the horizontal portions of this curve are different generating units. And so this firm has one unit that has a capacity of 920 megawatts. That's the first part of the horizontal of this offer curve. The first horizontal bit, 920 megawatts. That's the capacity of their first unit. And they're willing to supply that 920 megawatts at zero marginal cost. So they, or $0. Their supply is, they're willing to supply this for free, essentially. Their next unit, they're willing to supply at $60 per megawatt, and they have a capacity of 430 megawatts that they're willing to supply at $60. And then they jump up to $93, and they have some additional capacity, which is unspecified on this graph, but they're willing to supply, let's say, 100 megawatts at $93. And then we jump up again, and they're willing to supply another, let's say, 100 megawatts at $140. And then we can keep going. They have an additional, let's say, 75 megawatts that they're willing to supply at some unspecified amount above $140. Let's say roughly $245. And then finally, their last bit of capacity, is maybe another 430 megawatts, which they're willing to supply at $400 per megawatt. So that's firm 1. Firm 2, this is another generating station. They might have a different supply curve or a different offer curve. This might be firm 2's offer curve. So they are also willing to supply a bunch, an unspecified amount, let's say 400 megawatts at $0 per megawatt. And you can see they have many more smaller generating units, or many more small bits of capacity they're willing to supply at an increasing price. So this is essentially their supply curve, firm 1 and firms 2 supply curves. The system operator uses offer curves to determine the equilibrium price. The system operator, or the ISO, takes willingness to supply curves or offer curves from every firm and calculates an aggregate supply curve for every hour of the day for that particular market or that grid. This is a horizontal summation. The point at which demand crosses this supply curve will determine price. All offers below this price get to produce, but all offers above the price obviously don't get to produce. All generators receive the market price. The price of the last accepted unit sets the price for everyone. So we'll see examples of this in the following slides. Okay, so here we have the two firms' offer curves on one graph. The system operator uses the offers to determine a price. So now we're going to take both firm 1 and firm 2's offer curves and we're going to horizontally aggregate them to create the aggregate offer curve or the supply curve for the market. So in this case, the individual offer curves are in light blue and the aggregate offer curve is in dark blue. So let's look at what firm 2 is willing to offer at $200 per megawatt hour. They're willing to offer 835 megawatts. That's that dashed horizontal line there. Now, firm 1 is willing to, at $200 per megawatt hour, is willing to offer 1,650 megawatts. So that's how far out firm 1 is willing to offer. And then firm 2 is willing to, again, offer 835 megawatts, and then the sum of those two is where our aggregate offer curve of the dark blue line is at $200 per megawatt hour. So this is what's happening in every dollar. We're horizontally aggregating so that we get both firm 1 and firm 2's willingness to supply at a particular price. So here we have the aggregate offer curve. Here we have the inelastic demand. Remember that demand for electricity is extremely inelastic. And that's because retail prices are fixed. Customers are not seeing changes in the price, so they have no incentive to change their demand. So the demand curve is perfectly inelastic. In other words, as prices change, consumers do not change their demand. That's why it's vertical. So the ISO takes the demand and the aggregate offer curve, intersects it, and that's what delivers the equilibrium price. So in this case, the system demand is 4,400 megawatts. The aggregate offer curve intersects that at a price of $120 per megawatt hour. So that is the equilibrium price in this market for this particular hour or minute. So you can imagine this demand curve is going to be shifting around, and so will the supply curve. And so this price is going to change for every minute of every day. The intersection of these two lines is going to change every minute of every day. So the wholesale price is fluctuating, but the retail price is not. Firm 1 generates where the price crosses its offer curve. So the system average price is $120 per megawatt hour. We'll go back to firm 1's offer curve and we find where that intersects, where that price intersects its offer curve, and we find that firm 1 is going to generate 1,500 megawatts. That's where it intersects its offer curve. Everything above that price, it will not dispatch it. So if anything to the right of 1,500 megawatts, anything to the right of 1,500 megawatts is not dispatched, it's not being used, but anything to the left is being dispatched. Firm 2 will do the same thing. We're going to intersect the price, $120 dollars per megawatt hour, with the firm 2's offer curve, and we find that firm 2 is then going to be supplying 785 megawatts. So electricity prices during the day can be quite volatile. We talked about this on the previous slides, but let's talk about it a bit more. Each generation technology has a particular cost structure and production profile. So wind and solar have zero fuel costs. You know, wind and sun are free, but they have intermittent generation. We introduced intermittent generation in the previous lecture, and what it means is that those don't necessarily supply at all times. It depends on the wind blowing and the sun shining. Nuclear power plants have low fuel costs and stable production profiles. So nuclear power plants are pretty nice. The problem with nuclear is they can't ramp up very quickly. So if demand shoots up all of a sudden, then we can't ramp up a nuclear power plant to meet that additional demand. And then we have coal, natural gas, and even some oil. These have higher fuel costs, but they can ramp up and down more quickly than nuclear. Demand varies during the day and intersects the aggregate offer curve at different prices. So this is what I was saying about the demand curve shifting around, and same with the supply curve shifting around to create different prices at different times of the day. So that was the introduction to wholesale competitive electricity markets. Now for the next class, I want you to read Do Americans Consume Too Little Natural Gas? An Empirical Test of Marginal Cost Pricing by Davis and Mulligar. Just read the introduction, the background, and discussion of possible explanations, sections 1, 2, and 5.